Hello, everybody. My name is Mac. I'm from DTU, and I have a little bit on lifting line stuff for today. This is my pet, especially for anything kite related. So what I promised to do was to look into some kind of how does the lifting line aerodynamics line up with when we try and fly a kite at a prescribed path. And then for a conference like this, you make up the story much earlier than you actually make the results. So this will be kind of investigation somewhat related to that. So here's an outline, and I have 1 million slides. So I'm just going to jump directly into it. So why would you use lifting line for kite aerodynamics? And it's simple, it's fast, and that is really something that sells a lot, because I'm from normal wind energy to mostly that, and we still use methods that are 100 years old because they are simply so much faster than CFD, even though CFD can do a lot local stuff. A lot of stuff is still done with simple models. So if they perform reasonably well, they will be used a lot. So the pros are it's fast. You split the problem into a 3D and a 2D problem, and the 2D problem you can calculate with a fancier method or use 2D airfoil data for tunnels. And then you can use it for optimization. So you can, if done correctly, you can have the features of curved wings and own wakes that is curling up and unsteady stuff if you do it correctly. The cons are that it's tricky to do stalling stuff. So that's in a nutshell what it can what it can do. So in a nutshell, a lifting line model is something that you split into an outer model and an inner model. The outer model takes the shape of the wake, the overall shape, the layout of the kite in space, and it's a vorticity-based formulation. And the inner problem is airfoil data, what is felt by that. And I talked about this at WESC in 2023, and had something. I made my versions of how I think a lifting line model should be implemented, and I'm going to run through cartoon style of the performance of such a model. What these next 10 slides will show is there's a setup, and this is like an elliptic wing of a high aspect ratio, and then the next slide will show the performance. And there will be different ways of implementing a lifting line model. So all these fancy colors are different models found in literature, how to implement lifting line. And the one I suggest is blue, and my reference model, a vortex lattice model result, is black. So whenever a blue thing is close to a black, that means that at least the way I suggest seems to be working well. So the airfoil data I use in my model then is just 2 pi alpha lift and 0 drag, because it's a vortex lattice method thing. So here on the curve to left, you see as function of span length, local lift. On the curve to right, the local drag. And they agree well here. High aspect ratio elliptic wing, low aspect ratio elliptic wing, they agree well-ish. High aspect ratio rectangular wing, they agree well. Low aspect ratio rectangular wing, they agree well. And when you can't see the blue curve in the left curve, that it is because it's completely on top of the black one. And heel drill, now you start bending stuff. Still it performs reasonably well. You sweep it, it performs well. You sweep and heel drill at the same time, it performs well. You take an heel drill wing and move it such that what you feel on this side of the airfoil is not what you feel on the other side. So it's a steady state solution, but still you get that, and you even get the induced drag correctly evaluated on the wing itself. So you don't have to do Tref's plane analysis, which you can't really do in an unsteady setting anyway. So ideally you can use it for moving things also. So I tried to then set up a case with more than one wing, because the model can't do that. Everything feels everything else in the model. So if you have a main wing and some tailplane, horizontal, vertical tailplane, you can model that. So this is the artist's impression of something of like an Ampix AP2 model. And this is an artist's impression. I got data on the main wing, but I really didn't get data on how the tailplane looks and what the airfoils are. So it's something I guessed from pictures. So this is when the wind comes from straight ahead, and when I then start to flap the ailerons and the vertical wing at the back, you can see that the aileron changed the loading on the main wing, so I get more load on one side and less on the other. And when I flap the vertical wing in the back, I get the side force, the whatever color that is. And what you can see is that that influences the load on the horizontal wing. So everything is coupled here. So it's a fancy model that takes all physics more or less into account. So the crosstalk from the model is inherently modeled. So what I wanted to do was trying to take a lifting line model and then compare it to something that's used a lot in the kite community. And before knowing anything about really, and this is a confession, I really didn't look much into what was actually the model in Airbox, but Airbox has been mentioned 50 times at least at this conference, so it's something used a lot. So I just wanted to benchmark how is my lifting line model stacking up against something like the aerodynamic model in Airbox. So this is what I'm trying to do here, and the test case is this that I showed before, the Ampix AP2 approximation. And I'm looking at situations that correspond to those seen from an Airbox path optimization that we ran, so like 10 meters per second at 100 meters height and a shear exponent of 0.3 and running the AP2 model. And then I get a range of angles of attack, side slip angles, control surface deflections, and airplane rotations. And this is really what the model uses as input. And by the way, I should mention that my lifting line model is only a step on the way. So it's not it's not unsteady at all, actually. It's quasi-steady, just like the model in Airbox. But I'm trying to compare these two to see how things stack up. And I was hoping that a lifting line would be superior in some sense, of course. This is the track that I'm flying in, and then this is the angles of attack, control deflections, and side slip angles. And this is the rotations in space of the airplane. So these are plugged in, and then we can get a range of data, and then we can compare whether we do well or not. That's what the inputs are. And this is the Airbox model, just to explain you what that is, because I didn't know what it was, and it turns out to be, let's say do I have a pointer of some sort?
It doesn't work.
No, okay. So these are the dimensional forces. These are non-dimensional forces, and this is the dimensionalization. These are the non-dimensional force terms, and there's an equivalent for the moments here. And there's the first bracket that you get is the angle of attack only. The next is the angle of attack combined with a side slip. The third bracket with 9 elements in is the rotations. The last one is the control surface deflections. And each of these things, coefficients with an angle of attack, is actually calculated like this thing over there. So each of these actually have 3 coefficients. So in total, you have 48 coefficients with 3 coefficients inside of each of them. So in total, you have 144 coefficients in this model. So that's a lot of coefficients. And in the paper I refer to, they have a reduced set with only 75 coefficients. And this given set can only be used to model this setup. So if you can scale it up and down, but if you bend the wing, you have to make new coefficients. So that was kind of that's kind of how it goes. So you cannot use this kind of model to evaluate whether you want a bent wing or not. So that was kind of a aha moment for me. But how do we stack up then? So I run 6,561 cases with combinations of all these input parameters. And then I run lifting line stuff, and I run the Airbox aerodynamic model, but with coefficients that I extracted from my lifting line model, such that I'm comparing apples to apples and not apples to the coefficients found in a paper of something with a slightly different geometry. So this is modeling, checking whether the models, how well does the model stack up? Because the lifting line model takes everything in a nonlinear way, you could say, into account. And the depressing result is here. So I'm looking at standard deviation of the difference divided by standard variation of the result from the model I think is the best one, the lifting line one. And what you see here is that it's incredibly close. So it just turns out that 144 elements is enough to reduce, to really model this kind of behavior if you only look at this shape. So the nonlinear stuff going on in the lifting line model must be quite limited. And so a word on the speed here. The lifting line for a single simulation, which may not be a fair way to assess whether a lifting line model is fast or not, because a lot of the time is spent setting up the problem, but it's about 5,000 times slower. So if you are just going to do simulations of a given shape in space, this seems to be a really good approximation. If your lifting line model is not really a true unsteady model anyway.
Can you shorten it a
yes,
little bit?
Yes, I will. Yeah. So if you do a simpler one with just a table lookup, it doesn't look so well. So an Airbox model seems to be working well. But the thing that a lifting line model can do, you can add turbulence. So that's not really possible in Airbox. So when if you input turbulence corresponding to about 4% turbulence intensity in this case, then you get somewhat different results. So that's the added benefit of having a model that can do more fancy stuff. But it is 5,000 times slower. Even though you might actually, it would be possible if the turbulent fluctuations are large enough, you could approximate them with linear variations, and then you can make an equivalent turn rate of the airplane, and then you're good at going with Airbox. So conclusions: we compared models, and if you are only comparing a given shape, performance of that calculation model, you should actually go with the Airbox type aerodynamic model. And what is this like that? If you do a simpler model with only a table lookup, not including the rotation rate, you're not so well off. And you can include spatial turbulence in the lifting line model, which is nice. But the real thing I want to get at some point, and now we have funding starting soon, I would like to really make a really truly unsteady version of this lifting line model, because that's really the thing that is needed. This is a quasi-steady model, so I'd like to go to fully unsteady, but in the lifting line realm, that can be done like a fast-ish model. That was what I had to say.
Thank you. We are somewhat in time. Actually, we used apparently 2 presentation slots, so we just skipped one over, the one that was missing anyway. But are there questions? Aerodynamics, yes.
Thank you, Mike. Very interesting. My suggestion is that indeed, when you have the lifting line, by the way, we have also done with Jean-Baptiste models where we use the lifting line, which, as you know, has the difficulty that from the trailing edge to infinity, you have these straight vortices. And you would like to have them more complex, like helical, whatever. So at the end of the day, I think that when you come to having a lifting line that you want to put in the CFD solver, where you can have very complex wakes, like what we do for wind turbines or also for the AOS, at the end of the day, you come up to the conclusion that the lifting line becomes an actuator line method in the CFD solver, yes. And then you shed the vorticity from the actuator line method is a force that you put F in your CFD solver, and then the vorticity of that F will be shed in the wake, and it can also absorb the turbulence that you get at the inflow. So actuator line methods at some point become much easier to implement and use with turbulence than these lifting line methods, I think.
Yeah, there's
You have the problem of these trailing vortices. What do you do with them, right?
yeah, it can be tricky, and also there's some trickiness associated because it's singularities.
Yeah,
And
but
sometimes
we-
when
we
you bend a
smooth it, huh?
singularity, you get some other singularities than you can see in the numerical solution.
Yeah,
for
but that's
instance.
why the actuator line method basically is a modified version. We call that the modified lifting line method.
Yes.
And there is even a theory of the modified lifting line method, actually.
Yeah.
You can do the Prandtl lifting line theory with modification. So there is a sigma kernel on top
Yes.
of it.
Yes. Yes.
Thank you.
And that's one of the issues also, because then a part of the solution becomes quite dependent on the sigma, which is can be a little bit arbitrary. So that's one of the tricky things, I would say.
Okay, I'll talk to you more about that also later on.
Thank you. We have here Oriol.
Hi, Mike. Thanks for the interesting talk. You mentioned that the comparison with these 140-something coefficients is pretty in line with the lifting line. Do you expect that to be true for more unconventional geometries, let's say with higher neutral angles, for example, like soft kites?
Good question. Yeah. I actually set up my lifting line model so I can press a button, and then 10 seconds later I have these 144 coefficients. So it's a straightforward thing to actually investigate. Yeah, good idea.
Would be interesting to know. Thanks.
One last question, if there is any. No, then thank you again, Mac, for this lecture.